All right, so today's presentation, it's entitled Spatio-Temporal Inference and Learning using multiple hypothesis testing and multiple change-point detection. And this is the tasting menu of the day. So I first to say something about why we do this type of research, potential applications for that. And then I will briefly walk you through some of the basic ideas of multiple hypothesis testing, because this topic is not necessarily taught in regular detection and estimation related courses. Then we'll move to sequential inference and change-point detection. And I first introduced these ideas using a single change-point detection problem. And then regarding today's topic, how to do change-point detection and multiple hypothesis testing in large-scale sensor networks and for performing spatio-temporal inference, we'll consider techniques controlling something called false discovery rate. Since we are dealing with really large-scale problems that are connected to cloud or fusion center by wireless connections, we need to also consider communication constraints for such problems. Then we have derived some analytical results about average detection delay, basically telling that how fast you can detect those changes. And obviously the hope is that you could detect those changes with minimal average delay. And then also how data efficient you are, kind of concept related to statistical efficiency. What's the average number of observations needed in order to make those decisions. And last, we'll consider multiple hypothesis testing in purely spatial domain using FDR control. And the idea there is that you would actually learn the probability models and also be able to interpolate the decision statistics in points where you don't have sensors. And by doing that, you could characterize the regions where certain hypotheses are in place or regions where the null hypotheses are rejected. So that's the plan of the day, and so we'll proceed with this plan. So we are interested in performing distributed inference in large-scale sensor networks. This type of massive connectivity, that's of course one of the concepts in 5G. But many other systems like modern radars, the Internet of Things, environmental monitoring, if you want to monitor air quality and so on, they rely on this type of large-scale sensor networks. Also seismic monitoring, agricultural fields, you could monitor the state of the agricultural fields using large-scale sensor networks. Then many cyber physical systems, our infrastructure in the society, like smart grids, smart buildings, and so on, they are packed with sensors that monitor the state of these systems. Also in the internet, you might think of monitoring intrusion in a computer system and detect that type of anomalies that are taking place. And maybe more recently, you could think of also monitoring the spread of an epidemic using this type of techniques. So we have a large number of sensors that are in distinct locations, and therefore we need to perform distributed statistical inference. And it's a sensor kind of observes a data stream in a continuous manner. So you have the streaming data coming in all the time. And then obviously the amount of data is such that you cannot necessarily process all the data simultaneously and in a single cloud, but you have to do it in a distributed manner. And then these sensors, they communicate their local results or inferences to a fusion center or cloud where the actual final decisions are made. By using this type of techniques, we wish to identify interesting areas that we are monitoring, sub-regions where you have some changed behavior, some anomalies, some deviated, unexpected or adversarial events. And at the same time, you wish to control the error levels in decision making. Furthermore, there are quite a few time-critical applications where the inferences need to be done with a provably minimal average delay. And you also wish to come up with techniques that are sample efficient, so that with as little data as possible, you reach the quality of decisions you are aiming at. And for that purpose, we will consider multiple change-point detection. So here are some examples that where you have sensors in different locations, and then they communicate some local information to the cloud or fusion center that then fuses these informations and makes the final decisions. And then based on those decisions, it may take some actions. There's a picture that the sensors are in distinct locations, and then you wish to, for example, characterize these greenish areas here that where you have some change in the behavior or some anomalies or the probability model has changed. One prime example being the radio spectrum, if you want to identify the areas where the spectrum is being either idle or unoccupied, or the spectrum is congested or even contested. And then you may want to also figure out the boundaries of those regions, characterize where those regions are, and then you could use that. If you know those boundaries, you could use it for example for scheduling users or giving access to spectral resources and so on. I try to convey that's just the basic ideas here, and some of the gory details will be missing. But if you want to really go through technical derivations of the results and so on, and detailed explanations, these 3 papers cover these topics pretty nicely. So there are 2 papers that are being reviewed right now. The third one is basically accepted already, but we have to do a minor revision on that paper. So just in case you don't know your multiple hypothesis testing, just a brief tutorial. So there are kind of a number of applications in inference that you need to perform a large number of simultaneous hypothesis tests. This topic area probably is most commonly used in genomics, that there may be a large number of genes causing certain type of health condition, and you could use this approach for testing such purposes. In general, you are dealing with problems where you have multiple probability models. You may have multiple alternative hypotheses or multiple causes for rejecting the null hypothesis. At the same time, you may also have multiple data streams. That's of course the case in this large-scale sensor network problem that we are dealing with. So there are many signal analysis problems, medical testing, environmental monitoring, radio spectrum monitoring, financial data streams. You could think of, for example, co-integrated data streams associated with certain stocks or stock pairs and so on, and in general in data science. Having very high detection probability, and the statisticians would of course talk about the power of the test. It's important in these applications, because in many cases you are basically in the gray area between deciding between the hypothesis and choosing the alternative hypothesis may not be that obvious choice. At the same time, you also need to control the type 1 errors, false positives, and that is challenging in this type of scenarios. Some justification why to use multiple hypothesis testing. That if you are performing M hypothesis tests, then you may ask what's the probability of at least getting one false positive. So, and this is a very classical example that if the probability of making an error is alpha here, then obviously the probability of not making an error will be 1 minus alpha. and then probability of not making an error in M tests would be this 1 minus alpha to the power of M. And then if you want to figure out what's the probability of making at least one error in these M tests, it's given this 1 minus alpha to the power of M. And then if you evaluate this with different values of M, you will see that it gives you pretty bad news. For example, if you have 20 hypotheses to test, and you, just like in many statistical testing scenarios, you determine the significance level to be 0.05, then the probability of making one false positive or coming up with one false positive would be 0.64. So very high probability, even though its individual test would be non-significant. So that could be served. That kind of serves as a justification that if you really want to control these false positives using multiple binary hypothesis testing tests, it may not be the right way to do. And this figure just illustrates that that on this we have the number of hypotheses on this x-axis, and in the y-axis the probability of getting at least one false positive. And you see that already with certain, for example, with 60 hypotheses, the probability is basically 1 already, or very close to 1. So this motivates that the testing should be done somehow else. Just to describe some of the jargon that will be needed later on. So you could think that we have a null hypothesis and alternative hypothesis, and then if you kind of accept this alternative hypothesis or reject the null hypothesis, then you talk about making a discovery or calling this a significant one. And if so happens that you reject the null hypothesis, but null hypothesis happens to be true, then you make a type 1 error. And then total number of hypotheses that you reject, basically, or where you accept the alternative hypothesis, denoted here by R. And these two numbers will be used later on quite a bit. And there are a number of different criteria for controlling type 1 errors in multiple hypothesis testing. Maybe one of the best known is something called family-wise error rate, which gives you the probability of making at least one type 1 error. But today we'll be considering something called false discovery rate, and basically it controls the expected proportion of type 1 errors among all the rejected hypotheses, where you have selected that some alternative hypothesis is in place. So this false discovery rate is kind of rather well known in multiple hypothesis testing and widely used. And indeed, you want to control the proportion of these false positives, denoted by V in the previous table, among all positives denoted by R. So R is the number of all rejected null hypotheses, and V is the number of incorrectly rejected null hypotheses. And the FDR, you want to control then this rate, so setting some kind of a maximum allowed proportion for these false positives. This FDR concept, it was formally described by two statisticians from Israel in 1995. And more formally, this FDR is defined by the expected value of V over R, assuming that R is positive, multiplied by the, or given that R is positive, multiplied by the probability of R being positive. And then there's a variation of that. This is this positive FDR, where we make an assumption that R is positive. And this famous Benjamini-Hochberg procedure for FDR works as follows. It relies on p-values. And just in case you don't remember what p-values is, that basically means that what's the probability of getting observational test statistic that is at least as extreme as the current observed one. So basically you are looking at the tail probability that how much what's the probability of getting even more extreme value for the test statistic. And basically, if you get very small p-values, they indicate that there's very little support for the null hypothesis. And then you think that you receive get m of these p-values, and then you in order to do this inference, then you would rank order these p-values, and then you look for the highest rank denoted here by G, for which the p-value is less or equal to this J over M times this, in this case, delta, which basically gives you the how much of these proportion, how much you allow these false positives. And then the test from test 1 in this ranked order p-values, tests from rank 1 to rank J are declared significant, meaning that for those tests you will reject the null hypothesis. Well, these p-values, they have some interesting properties. That first of all, the p-values associated with the null hypothesis, they obey a uniform distribution between 0 and 1. And then the p-values that are associated with the alternative hypothesis, they are highly concentrated close to 0 towards the small values. And then you typically would observe a mixture of these two, and that is commonly described using kind of a beta uniform mixture distribution, where the beta distribution is used to model these p-values associated with the alternative hypothesis, and the uniform part is associated with the p-values associated with the null hypothesis. So you could use this type of beta uniform mixture to describe this the distribution of p-values. So that was a quick and dirty review of multiple hypothesis testing and how p-values are used in that testing. So then we'll move towards the kind of our work, which is multiple change-point detection in large-scale sensor network. And we have developed a few different techniques for that purpose, but today I will be talking about a technique called improved sequential map procedure. It's an improvement over the sequential map procedure that we came up with earlier. So change-point detection in general, that you have again data streams that are kind of streaming at high rates, and then collecting all this data and performing in offline inference is not really feasible. Furthermore, it's very important to detect rapid changes in these probability models, because you cannot necessarily preserve all the data, but you can basically tell when the data or the nature of the data has changed. And the change may be due to some anomaly, adversarial activity, or just that the phenomenon you are interested in has undergone some change. And what change-point detection does, it wants to find a stopping time denoted by capital T, and basically at that point we will decide that the change has taken place at some time instance T earlier. And then, so we are basically designing this type of stopping rules denoted by capital T. And your stopping rule will be optimal if you are managed to detect the change with minimal delay while maintaining certain false alarm constraints. So you impose a limit on the type 1 errors. And false alarm in this context would mean that you declare change before the change actually happens. So this, in such cases, this capital T would be smaller than this small t. And just some scenarios here that, for example, if you are monitoring radio spectrum, so one of these radios becomes active here, and then the sensors that are surrounding it, they gradually start to detect those changes, and they kind of communicate with the fusion center or cloud, which would be represented by the base station here, and eventually the base station will basically make a decision that the change has taken place, and it could also then characterize these regions where the change has actually taken place. So just to convey these ideas of change-point detection, I'll walk through the single change-point detection problem first. So we have discrete time observations, and the data comes from some distribution F0 before the change takes place, and from another distribution after the change has taken place. And since we have a Bayesian problem formulation, we will also have a prior on these changes, and a very commonly used prior is geometric distribution. And in Bayesian change-point detection, what you basically do is you come up with a technique to update the, as you observe these data streams, come up with a technique to update the change-point posterior probability. What's the probability of a change after you have observed the data? For this type of kind of real-time problems, you wish to have a recursive formula for that problem, and the recursive formula for the single change-point detection problem is given here. And in this example, since we assume that we know the probability models, we are using likelihood ratios in this recursive form. So you have the likelihood ratio here, and then also this prior model, and then the previous a posterior probability for the change. So this rho here is related with the geometric distribution, and so you could also use p-values for similar formula here, but just to illustrate the idea, likelihood ratios are used. And then regarding this performance of this type of techniques, you usually want to consider the average detection delay, which is of course the expected value for the maximum difference between the time point capital T when you detect the change and lowercase t when the change actually happens. So you want to have, of course, this difference as small as possible. Depending on the applications, the meaning of this would be different. So, of course, if, for example, the problem is monitoring the radio spectrum for flexible spectrum access, that the longer time you have a chance to detect that the spectrum has become occupied, the more you would cause interference to everybody else, and everybody would have to retransmit their data and so on. And as a result, you would consume a lot of spectrum and cause a lot of retransmissions there. Then the probability of false alarm is of course means that you declare a change before it has actually taken place, and then of course that would basically mean that you detect or think that the spectrum is occupied even though it's not, and therefore the spectrum would remain underutilized for that purpose. Okay, so that was the basic idea of single change-point detection, and then we move to multiple change-point detection. So, of course, again, you could think that if you would do multiple binary hypothesis testing and use that, but I hope I managed to convince you with this multiple hypothesis testing ideas earlier that it's not the way to go, and because, of course, this probability of getting at least one false alarm will increase very rapidly as a number of tests will grow. So we'll consider this false discovery rate concept for controlling the false alarm in this context. And since we have multiple sensors that are monitoring and producing, acquiring many data streams at the same time, so of course these change points in different sensors may also take place in different time instances. And you wish to detect all these change points and with minimal delay and at the same time control this FDR and false positives this way. And we wish to come up with a technique where the average delay more or less remains the same, even though the number of data streams would grow. And that, of course, makes the systems scalable.
Question, Lisa?
Yep.
So is there any statistical assumption you make in terms of the change points of different sensors, given that they are spatially located, there might be correlations among them?
Well, we are here, especially if you want to do any analytical work, you have to assume independence. But of course, the field of interest, there may be some correlations. But since the sensors are distinct sensors, the sensor noises and so on, they will be uncorrelated. And then depending whether you are using a stochastic or deterministic model for the field, then that of course impacts the correlation model. But the sensor noises are basically will be independent, and therefore you could use that as a justification for independence.
Okay, thank you.
Okay, so there's some earlier work that with Vince Poor and his colleagues that they have done some work where they are monitoring multiple data streams in parallel in different, very different contexts that we are considering. But in this type of massively connected wireless sensor network problem, that may not be feasible because you cannot send all the data points to the fusion center and monitor all these streams simultaneously. That you have to do something to deal with this spectral efficiency and so on for this problem. And in fact, what we want to do is to impose some communication constraints on this problem. We also take a Bayesian approach to the problem because it allows you to do also some analytical work and the deterministic problem formulation may not be feasible then. There are also other ways that you could basically control this amount of data to be transmitted. You could design sensors or sensing algorithms in each sensor, and then the sensor itself would decide whether it's sending its information to the fusion center, depending on whether the statistic is considered to be informative. And this approach is called censoring. So you would only censor if the local statistic would be informative, and as a result, you could really radically reduce the amount of information to be transmitted. Or you could use reinforcement learning, mainly multi-unbanded problem, to select which streams to monitor and basically design your reward function so that you would basically find the best streams to monitor, or streams that where it's more likely that change will take place and monitor those streams. There's some prior art on this type of change-point detection problem listed here. I won't be going into more detail there. So anyway, regarding this system model, as I mentioned already, we are considering large-scale sensor networks, and the sensors observe their environment all the time. And the Fusion Central Cloud could receive data from each sensor, but it wants to somehow control the amount of data and therefore the Fusion Center will basically select the sensors to be monitored. And each data stream, there's a kind of a random change point is associated with these data streams. And then the Fusion Center, in order to control the amount of information transmitted, it will select these active sensors or data streams to be monitored. And of course, those sensors that you want to monitor are such sensors where the change has not taken place yet. typical information that each sensor would communicate to the fusion center, or of course you could communicate all the observations. That would be very inefficient, but you could then think of compressing that information without any loss, and that of course means that you would communicate sufficient statistics. One example could be that you could communicate local likelihood ratios, and then of course under the independence assumption, then it would be very easy for the fusion center to combine these local likelihood ratios. Or you could communicate p-values or z-scores and so on. Okay, so the sensor will communicate to the fusion center only if this fusion center decides to receive observations from there. And the idea here is that we will just monitor a subset of sensors, but and then the subset of sensors is selected so that the posterior probabilities of change are very high for those sensors. And the idea also that of limiting communication, it will reduce this other important performance criterion, the average number of observations, which was associated with the data efficiency. It will also improve that. And then the idea is that you would come up with a technique that minimizes the average detection delay and also is very data efficient in terms of the average number of observations criteria. And so what we have done is to propose this Bayesian multiple change point detection procedure, and that takes into account this communication constraints. And the idea is simply that you will just monitor those sensors which have the highest probability for this change to take place. And at the same time, you wish to control the false discovery rate for this decision making. And we will have also established results that these procedures are scalable, so that this average detection delay and average number of observations do not increase, even though the number of sensors would grow. In fact, this will be constant that are independent from the number of sensors. It also happens that you cannot maximize or fully optimize simultaneously this average detection delay and average number of observations, especially because they kind of depend on the proportion of the sensors that you are monitoring. And we've been characterizing the trade-off between these two factors. So just to give you this formulation, so we have k independent data streams, and then in each data stream there's a change point, so typically the prior models for those change points obeys the geometric distribution, but it could be something else too. And for analytical work, that we basically assume that this data before the change, it comes from some distribution f0, and after the change, it comes from distribution f1. And regarding the question about independence, so we've been based on the independence of noise, we basically can claim independence here. But of course, these actual fields can be correlated, and if it's a physical phenomena like radio waves and so on, that there may be or some air quality or weather pattern and so on, there may be some correlations in the field. Anyway, this type of formulation allows us to come up with some or derive some analytical performance guarantees bound to these detection delays and average number of observations and so on. So if you do this multiple Bayesian change point detection, this recursive update formula for this a posterior probability of change looks like this. So we have basically two different terms here. One that is valid for the subset of sensors that you are monitoring, and it's based on these likelihood ratios and so on. But it could similarly, you could do it at least with p values that you are receiving from the sensors. And then for those sensors that you are not monitoring, this update is basically based on the kind of a posterior probability based on the previous observations, plus a term that follows from the prior model here. So you also update those posterior probabilities for the sensors that you are not monitoring, but that update is based on the prior model. All right. And then it's multiple change-point detection. So you want to basically find these multiple stopping times, come up with multiple stopping rules here. And then you may also have a deadline for these decisions. So you need to come up with a kind of a decision by some time instance in max here. And then B here, as earlier, it denotes the number of false discoveries. And so on. And then R is, of course, the number of change points that you have declared, and so on. So the FDR criteria is here. And then what the designer does, it specifies some upper bound for these false discovery rates. All right. And this average detection delay, of course, it's defined the way I described it earlier. Here it's given for individual data streams, but then you can also consider the average over all these data streams here. And similarly, this adaptive number of observations. And this adaptive number of observations, of course, it somehow captures the communication burden or communication complexity there. All right, so that the idea here is anyway that we will wish to minimize both average detection delay and average number of observations while controlling these false positives. Okay, so we will use the sequential formula that I showed you already to update these posterior probabilities for each sensor, and we will have selected some proportion of the number of sensors to be monitored. And this small q here denotes the proportion of how many sensors out of these K sensors are monitored. And then every time you update these formulas, then you basically choose the subset of sensors that have the highest posterior probabilities of change point having occurred. And then the actual FDR control basically is related to this famous Benjamini-Hochberg procedure that I showed you already. So you basically choose a threshold value Q or Q sub R for each data streams, and then you want to make sure that the a posterior probability is probability of having this a posterior probability larger than the threshold value is smaller than this alpha when this time instance is smaller than the actual time instance of the change. So the sampling state is described here. So you will basically sample a subset of these data streams with the highest, shown with highest posterior probabilities. And every time you have received these local decision statistics and so on, you will update the posterior probabilities and then again choose the subset to be monitored. And then if the threshold is, if the posterior probability is higher than the threshold value, then you declare that change has taken place and you take that stream off from the list of streams to be monitored. And then, of course, there's a deadline for this decision that if this, if you exceed this and max, then all the data streams that you are actively monitoring, that you will declare that no change has taken place and you stop the procedure. All right, but anyway, then the idea is that you will control this FDR and make sure that it remains smaller than the threshold value you wish to have. And then you will control this, or we will also investigate this ADD-ANO trade-off. But I will just show you that then we have established results on the lower and upper bounds for this average detection delay. Of course, the lower bound is basically associated with the minimum detection delay, and you wish to reach that lower bound. And upper bound is basically just describes that if you rely on the prior model, that how long it would take place that based on the updates that you would exceed the threshold value. The most important result here is that these bounds they are basically constants, which guarantees that the process is highly scalable. And we have also established similar upper and lower bounds for this average number of observations. And then one important factor is that what's the impact of this Q, i.e. the proportion of sensors you are monitoring. So if you have a kind of low proportion of sensors, then it would mean that the detection delay would grow, but at the same time, you'd be very data efficient. And so as a result of these analytical studies, that the asymptotic average number of observation bounds are linearly increasing with Q. And on the other hand, these detection delays, they are decreasing with the increasing Q. And therefore, there's kind of trade-off between these two. So how to design this Q such that you could do both really well. And but you can, of course, come up with a weighted risk that you somehow weight how much you are willing to suffer in the detection delay and how much less data efficient you are. And then based on that risk, you could come up with a procedure that performs this trade-off. It's a simulation example that we are taking different proportions, 20 different proportions here, and study how the system behaves as a function of Q. And if Q equals 1, it basically means that it's a fully parallel procedure that every sensor sends all the data to the fusion center. Then we use a very commonly used FDR upper bound 0.1. And use this geometric distribution as a prior model with the parameter rho equals 0.01. And then we have some other procedures used for the comparison purposes. Basic result is visible here that for this IS map that is the lowest here, then it has basically the lowest detection delay, both for the case where you are monitoring all the sensors and then you are monitoring only half of the sensors, and then the other techniques do much worse. And you can also see the fact that this kind of constant, this detection delay is constant even if the number of sensors increases. A similar result for the average number of observations, that the procedure that we propose, it has certainly, and in this case, of course, it's beneficial to have Q much less than 1. So these processes that are using Q equals 0.5 will have need much less data to come up with these decisions than the processes that use all the data. And then we have studied this ANO-ADD trade-off and tried to find a sweet spot for this Q. So we have also done this similar recursive computation using the p-values, and you recall that the p-values, that the probability model for them is this beta uniform mixture, and then for the p-values that come from the alternative hypothesis, you use this beta part, and then p-values coming from a probability model associated with null hypothesis, they would follow a uniform distribution. So you could use those in order to come up with similar recursive formula for updating this. And then you can study this ADD and and come up with very similar results that usually saw with the likelihood ratios there. Okay, so that was a weak walkthrough of this change-point detection, but then maybe more kind of detailed study about spatial domain inference using FDR control. And for that purpose, we assume that the spatial region that we are interested in, it's subdivided into discrete grid points, and we have Q of those grid points. Sorry about the notations. It's not consistent, but because Q was used for other purpose earlier. And then we have a null hypothesis where we think that the signals are in nominal state there. That null hypothesis can be different in each sensor location because so the phenomena may be different and the sensors may be heterogeneous and so on, but that we don't assume that there would be a single null hypothesis in every place. In fact, what we do is that we learn this distribution under null in each sensor. And then there's some alternative hypothesis that basically describes the case where some deviation or anomaly compared to the null distribution has taken place. And then we wish to kind of identify the points in this grid where this alternate hypotheses are in place and basically characterize their boundaries and so on. And also the area between the sensor locations to figure out where this hypothesis is in place. And of course, there are many reasons and so on for these changes, and therefore we use this multiple hypothesis testing approach for and try to control this proportion of false positives to all positives. So we assume that we have n sensors here, and each sensor will now learn its local statistical model under H null. It's basically meaning that your sensor could, for example, observe noise only in its location, and there's no signal present there. And then the sensor is able to condense the observed information into local p-value, and these p-values are communicated with the fusion center or cloud. And in the cloud, then it's you compute this probability of local decision statistic coming from this null distribution for each grid point. And then you wish to subdivide this or segment these areas into areas associated with the null hypothesis and with alternative hypotheses such that this FDR control is strictly enforced. And the idea is that you could basically localize or characterize these interesting areas precisely. And at the same time, you could limit the communication between sensors and cloud and also deal with spatial signals and the fact you are learning these local distributions and so on. It allows you to accommodate heterogeneous sensors and at the same time get the peace of mind by controlling the false positives. The actual process is, the stages are described here. So at each sensor, you would have a training phase that you learn the probability model of local test statistics under H null. So you could use kind of empirical modeling. And then the actual operational phase when you observe these phenomena and so on, that you will acquire the observations and then you compute the local test statistic and then you would compute the local p-values. And then the actual learning that you will actually learn these p-value distributions. And we are basically using this type of mixture distribution where you have a uniform component and then you have multiple of these beta components to capture the p-values, small p-values associated with alternative hypothesis very accurate. And since this is based on a concept called local FDR, and we consider that it's kind of contextual local FDR because each sensor we are able to figure out the local distribution as well as the local priors and use that in this empirical Bayesian inference. And then in order to figure out what are the test statistics in between the sensors, then we interpolate this this contextual local FDRs to characterize these regions and so on. And since it's like an empirical Bayes procedure, then this spatially varying priors are also estimated on fly. And then finally, in the cloud, you will then do this multiple hypothesis testing based inference and figure out these kind of regions where the null hypothesis, all the alternative hypotheses are in place. So you will basically, the data that you are processing are the p-values from each sensor and that are computed locally. And then there's in each sensor you compute this contextual local false discovery rate criterion that are given by this expression here. But the contextual is because you need to estimate this local priors here as well as the distribution of the p-values under H or the alternative hypothesis. You already know that the p-values under the null hypothesis, they obey the uniform distribution, but you want to accurately estimate this distribution of p-values under the alternative hypothesis. And for that purpose, this empirical Bayesian approach is used. And then once you have those, then you can also, in each sensor locations, then you can interpolate them in between the sensors, and you could use kernel methods that we've been using in the examples today, or you could use Delaunay triangulation and barycentric coordinates. That would be more like a computational geometry based procedure for doing. So this is just some more explanation of the local FDR, but I just realized that we are running out of time, so I kind of well, just want to say that indeed we are using this mixture model of multiple beta distributions to capture the distribution of p-values under the alternative hypothesis, and for that purpose we use something called the spectral method of moments approach. So basically, you compute sample moments and then for any mixture and associate then with the parameters of these mixture components. And this method of moments, of course, requires that there's a mapping between the moments and the parameters of interest and one-to-one mapping, and we are using that type of mapping. And this method for estimating this p-value distribution under H1 is described here. So we have many different beta distributions that, and we are the small p-values. They kind of we assume that they obey a mixture of these beta distributions, and then we use this spectral method of moments to find out the parameters and mixture proportions of these beta distribution components. So you have L of these mixtures here and so on. And of course, the bad news is that there's no guarantee of optimality for it. It's not a kind of maximal likelihood estimator. An alternative way to pursue maximal likelihood would be to use the expectation maximization method for this type of mixture models. That is commonly used technique. But of course, there's no guarantee that you would find the global optimum, that you might end up with a local optimum. And then, of course, there are lack of tricks to deal with that issue with expectation maximization. But this spectral method of moments is a technique that is computationally very efficient and uses only 3 first moments. And it's originally used for multivariate Gaussian data, but we are using it for this beta mixture model. Just to illustrate some how this would work in practice. So we are all interested in monitoring the radio spectrum, and then of course there may be multiple active transmitters at the same time, and then you want to characterize those areas where the spectrum is being occupied by these transmitters. For the simulations, we assume that we have 100 by 100 grid points there, and we consider both line of sight signals and non-line of sight propagation. So line of sight would be of course that either direct path from the transmitters to the receivers, or from a Bayesian type of propagation model. And non-line of sight model would basically obey Rayleigh fading model. And then we average all these results over 200 independent realizations. And then these different methods for computing these local FDRs and this empirical Bayesian model for the p-value distribution are used in the examples. And it's just a case that we have 1,000 sensors in this, and then there's one source in this non-line of sight scenario, and then basically these red areas to tell where we reject the null hypothesis, and where this one guy would be using the spectrum there. And then at the same time, you also want to monitor that this false discovery rate remains under the nominal FDR requirement, and which was 0.1 in this case. And here you can see that the FDR is strictly controlled. Some of the methods are even too conservative in that sense, which is then visible in the detection power. But these methods do pretty well also in terms of detection power. And also some results about the FDR control, that you can indeed control this FDR, and then some methods are maybe too conservative. That you would like to push it closer to the nominal level to get higher detection power. But anyway, that you strictly control that. And there were some other methods that they don't necessarily cannot guarantee you the control of this false discovery rate, which is of course bad news, that because you want to have quantitative performance guarantees when you are using this type of technique. Then another example that where you have 8 sources and line of sight scenario, and then this technique will then identify these regions where the spectrum is being used. And again, you maintain this FDR control strictly, and then the technique that we have proposed here has also the highest detection power. So I think I'm kind of consumed my time. That of course there was a lot of technical detail missing, but I hope I was able to convey some of the key ideas about how to use multiple change point detection in spatio-temporal inference problems, and in case of large-scale sensor networks. And we used this multiple hypothesis testing and FDR control extensively, and then learned these probability models under null, as well as the distributions of the p-values that allow you to then set the threshold values and provide required FDR control. And then we have also established bounds for the average detection delay and average number of observations. And the key message there is that these techniques scale well, that this detection delay and average number of observations, they remain constant regardless of the number of sensors. And the more influential factor here is the proportion of sensors you wish to monitor. And that, of course, means that the fewer sensors you monitor, the less data you need to transmit, and the better average number of observations you achieve. But at the same time, it will, if you use only few sensors, it will add to the few active sensors, then it will add to the average detection delay. And then we also performed the spatial inference to characterize these regions where the alternative hypotheses are in place. For example, areas where you have a lot of bad air quality, you don't want to go biking there or walking there, or areas where the radio spectrum is being congested or contested, or in power grid, for example, areas where there's some anomaly or so on, or in the internet where some denial of service attack is taking place, and so on. It was very important here to be able to model the distribution of p-values accurately, and we used this spectral method moments to estimate this local FDR based on this beta uniform mixture models. And then in order to characterize these regions, we interpolate this contextual local FDR values in between the sensor locations and using kernel techniques. And again, here we achieved a strict FDR control. So that concludes my presentation. And if you have any questions and you are not in a rush to go to Thanksgiving events and with your family and friends, so I'd be happy to entertain your questions. And thank you all the troopers that came to the talk today. I know many of you would like to travel right now, but anyway, thanks for sticking around.
Thank you, Visa, for the very interesting talk.